The beginning of everything. Approximately 13.8 billion years ago, the universe came into existence. In one instant, there was nothing, and the next, there was everything. How this happened remains one of the greatest mysteries in science, bridging the gaps between theory and experimentation, physics and philosophy. Our understanding of the universe is built upon principles of causation, processes, and mechanisms, as we continuously seek to uncover the reasons behind existence itself. And yet, at its most fundamental level, we still do not know how or why the universe emerged. This uncertainty, however, is not due to a lack of investigation. Perhaps, as renowned physicist Stephen Hawking once suggested, there was simply nothing before the universe began. If space and time are intertwined as fundamental aspects of our universe, then their inception coincided with the birth of the cosmos itself. Without time, space could not exist, and without space, neither could the universe. Hawking envisioned space-time curving backward, contracting, and eventually rounding out, making any search for a prior state as meaningless as looking for a location beyond the North Pole. Alternatively, there may have been no true beginning, just a limit to our ability to observe. Many scientists believe that an initial burst of exponential expansion, called inflation, ignited the Big Bang and laid the groundwork for everything that followed. This inflation lasted for a fraction of a second before stopping, but some theorists argue that inflation never truly ended. It continues eternally in other regions of the cosmos, forming new bubble universes within an infinite multiverse. Another hypothesis, the Big Bounce theory, suggests that our universe is part of an endless cycle of expansion and contraction, rather than a one-time event. Instead of arising from nothing, as its conventional inflation models propose, this theory, championed by physicists like Paul Steinhardt, posits that the cosmos undergoes repeated cycles of growth and collapse. Perhaps our perspective on scale itself is flawed. Roger Penrose has explored how physical properties remain consistent regardless of size, and suggests that the universe might operate similarly. In this framework, time and scale dissolve at both the infinitely small and infinitely large, making them in some sense equivalent. A chess game follows the same rules, whether played on a tabletop or across an entire courtyard. Another possibility is that our universe resulted from the collision of higher dimensional structures. Superstring theory describes reality as composed of tiny vibrating strings within an 11-dimensional hyperspace. The familiar 3 dimensions of space and 1 of time exist as part of a single brain within a larger cosmic structure, with the universe's birth and expansion driven by the interactions of these higher order dimensions. Or maybe the answer lies somewhere beyond our current understanding, hidden within an unexplored corner of mathematics or physics, waiting to be discovered. For now, the origin of the universe remains an open-ended puzzle, a scientific choose-your-own-adventure. However, one fact remains indisputable. 13.8 billion years ago, the universe began. The hottest place in the universe. Where in the cosmos can the highest temperatures be found? A natural assumption might be the core of a star, where nuclear fusion rages. Yet even if you could withstand the searing descent into its depths, the effort would be in vain. Stellar cores reach a comparatively modest 15 million degrees Celsius. More extreme heat is generated during supernova explosions, where ejected gas shells reach temperatures exceeding 100 billion degrees. But even that doesn't set the ultimate temperature record. In fact, the hottest temperature ever measured wasn't found in the heart of a star, or during a cosmic explosion. Instead, it was recorded underground, beneath the snowy landscape near Lake Geneva in Switzerland. In 2012, at CERN's Large Hadron Collider, when lead nuclei were smashed together at nearly the speed of light, the resulting collision briefly reached a staggering 5.5 trillion degrees Celsius, 50 times hotter than a supernova, yet even this pales in comparison to the highest theoretical temperature. Temperature is simply a measure of a particle's energy, how fast it moves or vibrates. At the lowest extreme, absolute zero Kelvin, or negative 273.15 degrees Celsius, represents the point where all motion would theoretically cease. On the other end of the scale, there exists an ultimate upper limit, an absolute hot, beyond which particles disintegrate from their own energy. This is known as the Planck temperature, approximately 1.4 times 10 to the 32nd Kelvin. The concept is named after Max Planck, a German physicist who laid the foundation for quantum theory in the early 20th century. His work led to the idea of quantized light energy, or photons, and ultimately to defining fundamental physical limits. Using constants like the speed of light and gravity, Planck established the smallest measurable length, the Planck length, roughly 1.6 times 10 to the negative 35th meters, about 100 quintillion times smaller than a proton. The time light takes to traverse this minute distance is known as the Planck time, 5.39 times 10 to the negative 44 seconds. While these numbers are incomprehensibly vast or minuscule to human perception, they become crucial when examining the universe's infancy. Since the cosmos has been expanding since its inception, growing less dense over time, the conditions of its earliest moments can only be understood through Planck scale physics. Scientists remain uncertain whether the universe is infinite, but if it is, then it always has been. Rather than beginning as a singular point, the universe may have been infinitely large from the start. Instead of expanding in size over time, it would have simply become less dense. However, our observable universe is distinct. It represents the only portion of the cosmos that we can ever perceive or interact with, and likewise, the only part that could ever perceive or interact with us. This limitation is dictated by the speed of light, and the distance it has managed to travel since the universe came into existence 13.8 billion years ago. Rewinding time, we see that this observable section of the universe shrinks, growing increasingly compact, until we reach a moment when everything within it was just a single Planck unit of time old, its diameter reduced to a single Planck length. At this minuscule scale, the temperature of the entire cosmos would have reached the Planck temperature. It is perhaps unsurprising that this instant, 100 million trillionths of a second after space and time began, is referred to as the Planck era, and it was an incredibly strange epoch. Today, everything in the universe operates under fundamental laws of nature, controlled by four primary forces: the strong nuclear force, which holds atoms together; the weak nuclear force, which governs certain radioactive decays; the electromagnetic force, which distributes energy across great distances; and gravity. At the turn of the 20th century, physicist Max Planck theorized that the strong, weak, and electromagnetic forces could be quantized, meaning that they could be represented as discrete, indivisible packets of interaction similar to particles of matter. These so-called force carriers are known as gluons, W and Z bosons, and photons respectively. Gravity, however, behaves differently. With his general theory of relativity, Albert Einstein revolutionized our understanding of gravity, moving away from classical mechanics and redefining it as the curvature of space-time itself, a distortion in the very fabric of reality. Over the years, general relativity has been rigorously tested and confirmed through large-scale experiments, solidifying the idea that gravity-induced space-time curvature is an intrinsic property of the universe, influencing all matter and energy. During the Planck era, long before the conventional laws of nature had taken effect, gravity was the first force to emerge. But there's a fundamental challenge. Everything we currently understand about gravity is rooted in Einstein's theory, which has only been tested at large scales. In the Planck era, however, the entire observable universe was packed into a space trillions of times smaller than a proton, an environment where general relativity no longer provides useful predictions. Instead, the physics of such minuscule scales falls under the domain of quantum mechanics. At this microscopic level, the rules of physics shift dramatically. Particles no longer behave in deterministic ways. Instead, they exist in states of probability. Their exact locations can never be pinned down, and the mere act of observing them alters their behavior. Unlike the macroscopic world where things appear stable, the quantum realm is in constant flux. Fortunately for us, this strange quantum behavior is only noticeable at incredibly tiny scales. As objects grow larger, the randomness averages out, allowing the predictable physics we experienced in daily life to take hold. However, during the infinitesimal instant of the Planck era, there was no escape from quantum uncertainty. This incompatibility between general relativity and quantum mechanics presents one of the biggest unresolved problems in modern physics. Scientists are still searching for a way to unify them. A quantum gravity theory capable of explaining how gravity functioned in the extreme conditions of the Planck era. Unfortunately, testing such a theory through experiments is practically impossible. Current particle accelerators, like those used to study other force carriers, operate at scales far removed from the Planck era. In fact, to generate enough energy to properly investigate gravity under those conditions, we would need a particle collider the size of our entire solar system. Despite this, theoretical physicists continue to propose potential solutions. One idea suggests that, like the other fundamental forces, gravity may also have a corresponding force carrier, a hypothetical particle called the graviton. However, because gravity is much weaker than the other forces, detecting a graviton would be extremely challenging. Another approach, known as loop quantum gravity, takes a different perspective. This theory envisions spacetime as not infinitely smooth, but rather composed of discrete quantized loops at the smallest possible scales. By reformulating Einstein's equations in terms of these loops rather than continuous points, calculations become more manageable in a quantum framework. One of the leading candidates for a quantum gravity theory is string theory, which reimagines the point-like particles of traditional physics as tiny vibrating strings. The way a string vibrates determines its properties, including its role in conveying the force of gravity. However, making the math of string theory work requires the existence of at least 10 or 11 dimensions, many of which are thought to be hidden or curled up in complex structures known as branes. These branes are key elements of an even more elusive framework called M-theory. Each of these ideas presents an increasingly abstract vision of reality, relying on complex mathematics that is difficult, if not impossible, to visualize. Yet when we attempt to peer back to the first fraction of a second after the universe's birth, we are in effect trying to do exactly that. Picture a time when physics as we know it did not yet apply. Ironically, it was in the 1950s, when quantum mechanics was still in its early stages, that physicist John Archibald Wheeler introduced a striking image of what this primordial universe might have looked like. He described it as a chaotic and fluctuating quantum foam. This quantum foam arises due to the unpredictable nature of interactions at microscopic scales. Heisenberg's uncertainty principle makes it impossible to precisely define time, length, or energy at any given point within such a universe. As a result, space-time would not have been the smooth, continuous fabric we experience today, but instead an erratic, ever-changing sea of tiny fluctuations. In this wild, energetic environment, micro black holes and wormholes could have spontaneously formed and vanished without cause or consequence. For the briefest of instants, anything could happen. But this era of total unpredictability did not last long. After just 100 million trillionths of a second, the chaotic conditions of the Planck era gave way to the next stage in cosmic evolution. As the universe expanded and cooled, it began transitioning into a more structured state, one where our current understanding of physics could start to take hold. The universe would not resemble what we see today for quite some time. But from this point forward, scientists have a better chance of describing what took place. Since potassium is slightly radioactive, about 5,000 potassium atoms decay every second due to the weak nuclear force. Meanwhile, 150 million kilometers away, the sun's core is a burning furnace fueled by the fusion of hydrogen into helium. This powerful reaction not only keeps the Earth habitable, but also creates the elements that make up our planet, the television, and even us. And all of this is also governed by the weak nuclear force. Though it is weak, the weak force has a significant range. The four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, work together to shape our universe. This balance has remained the same for most of the cosmos's multi-billion-year history. However, in the very beginning of time, conditions were different, and the laws of physics operated under a distinct set of rules. During the Grand Unification epoch, which followed the Planck era, there were only two forces. But how could this be? To understand this, imagine flipping a coin. Initially, the coin is spinning, and it's impossible to distinguish whether it's heads or tails. It's only when it lands that you know the outcome. The same concept applies when we examine the behavior of fundamental forces at high energies. As the temperature increases in the early universe, the weak nuclear force and electromagnetism begin to blur into a single entity, the electro-weak force. If the temperature increases even further, the strong force combines with the electro-weak force to create the electro-strong force, a unified whole. This process, known as grand unification, hasn't been definitively proven through experiments, though high-energy collisions and particle accelerators point to the merging of electromagnetism and the weak force. For the strong force to join in, energies 1,000,000 times greater are needed. Even the most energetic events, like supernovas, aren't sufficient. As for gravity, whether it will be incorporated into this unified force is still a mystery that quantum gravity theories must address. The grand unification theory is a leading explanation for the universe's behavior just after the Planck era. For about 10 million times the duration of the Planck era, the universe expanded and cooled, yet it remains smaller than a single quark, the smallest known particle. Despite the tremendous energy in the universe, it had cooled to a temperature of 100 billion trillion Kelvin, significantly higher than what the Large Hadron Collider can achieve. This was the Grand Unification epoch, where particles transformed rapidly in the chaotic electrostrong field. In this era, particles like photons spontaneously created matter-antimatter pairs and transformed into quarks and leptons, only to decay back into photons shortly afterward. Under the influence of the electro-strong force, particles constantly change forms in an energy-fueled frenzy. However, after just a trillionth of a second, the universe began to cool enough for the strong force to emerge, splitting the forces into three and marking the end of this chaotic epoch. While these theories can describe the behavior of particles in the early universe, they fail to explain the universe's large-scale structure. When comparing the initial conditions to the present-day universe, the Big Bang theory seems incomplete. For instance, the average temperature of the universe is incredibly uniform, 2.7 Kelvin, despite the vast distances involved. This uniformity suggests that there was a thermal equilibrium in the early universe, which is difficult to explain given quantum fluctuations during that time. This discrepancy is known as the homogeneity problem, or the horizon problem. Furthermore, Einstein's general theory of relativity predicts that massive objects create curvature in space-time, influencing the movement of matter. On large scales, the imperfections in space-time smooth out, leading to what appears to be a flat universe. This flatness poses questions about the universe's overall curvature. Depending on the density of matter, space-time can either curve positively, resulting in a big crunch, or negatively, causing the universe to expand forever. Current measurements suggest that the universe is flat, which raises further questions about its future evolution. Similar to the horizon problem, the likelihood of this being the case is incredibly low, almost as unlikely as flipping a coin and having it land perfectly on its edge. For this reason, it has come to be known as the flatness problem. Furthermore, there's another issue that challenges our understanding of the universe's first trillionth of a second, the absence of magnetic monopoles. Throughout the universe, electric charges appear as positive and negative pairs, neutralizing each other to create a stable, electrically balanced system. Similarly, magnets always have both a north and a south pole, with magnetic field lines flowing between them to create a balanced whole. However, while isolated positive and negative charges are observable, such lone magnetic poles, monopoles, have never been found. No matter where we look in the universe, we've yet to encounter a singular monopole detached from its opposite. In December 1979, as he contemplated the mystery of these missing monopoles, theoretical physicist Alan Guth had a breakthrough. He proposed a solution not only to the monopole problem but also to the horizon and flatness problems. Rather than a gradual expansion over billions of years from a singular point, Guth suggested a mechanism in which the universe could have inflated suddenly and nearly instantaneously, expanding many times its original size before slowing and continuing its more conventional expansion. This inflationary phase would have caused the universe to double in size, roughly 90 times, in less than a trillionth of a second, resulting in an exponential expansion that dramatically reshaped the cosmos. Imagine folding a large sheet of paper repeatedly. If it starts out at a tenth of a millimeter thick, each fold doubles the thickness. After 7 folds, it would be as thick as a notebook. By the time you reach 12 folds, the paper would stretch over a kilometer in length. By 51 folds, it would reach the sun, and with 90 folds, it would span the size of the entire Virgo supercluster. This astonishing expansion mirrors Guth's theory for the universe. In less than a trillionth of a second, after the turbulent Planck and grand unification eras, the universe would have grown by an octillion times its original size. This sudden inflation is what provided the bang in the Big Bang. Although the universe may have seemed hot and full, it became vast, cold, and empty after this rapid inflation. This drastic change, however, elegantly resolves the 3 significant issues challenging the Big Bang theory. Inflation makes it possible to entertain the idea that the vast universe we observe today is not the entirety of existence, but merely a small, observable portion defined by the speed of light, and the expansion that has occurred since time began. Thanks to inflation, the horizon problem, which questions the thermal uniformity across the cosmos, is no longer an issue. The early universe could have contained extreme temperature fluctuations, which were then separated during inflation. Our observable universe only represents one small patch that was once in thermal equilibrium before inflation. Similarly, the flatness problem becomes less puzzling when we consider that we may only be observing a tiny fraction of the entire universe. The vast cosmos could be curved, either positively or negatively, but we simply cannot see beyond our local cosmic horizon. Lastly, the absence of magnetic monopoles is only a problem if we assume they should exist in the entire universe. In fact, if they existed in the early universe as our models predict, inflation would have spread them out so far that they are now distributed to a density of about 1 per observable universe. It's no surprise then that we've yet to detect one. Today, inflation is an accepted part of our understanding of the early universe, and scientists have spent the last 40 years refining the mechanisms by which such a rapid expansion could occur. The end of this inflationary period coincides with the cooling and energy drop that led to the end of grand unification and the emergence of the strong nuclear force. Some scientists suggest that the decay of X bosons, which carried the electrostrong force, could have produced a strong inflationary field, driven by a new particle called the inflaton. This energy would have fueled the universe's exponential expansion, creating large-scale structures from quantum-scale irregularities, leading to the formation of galaxies and superclusters in the modern cosmos. The universe would eventually cool, dropping in energy by a factor of 100,000. Scientists are still unsure of the exact reason inflation stopped, but when it did, the inflaton field decayed, releasing energy back into the universe in a process called reheating. This allowed matter to form, and with the universe now larger and less dense, the laws of nature could begin to behave in a way that we understand. This marks the electroweak epoch, which continued until about a trillionth of a second after the Big Bang. At this point, quarks, leptons, and all particles were influenced by gravity, the strong nuclear force and the electroweak force. But despite the high energies, the strong force had minimal impact on the particles, and the electroweak force had little control over their interactions. Gravity was present from the start, but until particles gained mass, it couldn't exert much influence. It would take another drop in energy and a cosmic transformation before the universe began to resemble the one we recognize today. Just as the human body has its heart positioned slightly to one side, the universe also contains imperfections in its seemingly perfect balance. Some particles always spin in one direction and never in the other. There is an uneven distribution of matter and antimatter, and electric fields can do things that magnetic fields cannot, even though they are theoretically similar. These imbalances are essential for the way reality functions. However, things were not always like this. In the first trillionth of a second, cosmologists believed that the universe was completely symmetric, with everything in perfect balance. But this symmetry was disrupted when the forces finally separated, giving rise to a new influence: mass. Just as lowering the temperature in water leads to phase changes, from vapor to liquid to solid, each transition altering the substance's properties and symmetry, so too did the cooling of the early cosmos trigger changes in the matter and energy it contained. As the fundamental forces broke apart and settled into distinct forms, a new era began. The quark era, where matter interactions first defined the universe. The largest object known in the universe, the hypergiant star UY Scuti, is composed mostly of the smallest particles, atoms of hydrogen and helium. While these atoms were once considered the smallest possible entities, we now know they're made of even smaller particles. Protons and neutrons, which make up atoms, are actually combinations of quarks. These quarks, alongside electrons, govern the behavior of everything, from the tiniest particles to the largest stars. For over 200 years, physicists have sought to uncover the fundamental particles of matter. This search involves smashing particles together at high speeds in colliders, where scientists analyze the aftermath to better understand the building blocks of the universe. This has led to the development of the Standard Model of particle physics, which explains the behavior of a normal matter composed of protons, neutrons, hadrons, and quarks. The Standard Model also includes 6 types of quarks and 6 types of leptons, along with antimatter counterparts and the force carrier particles: photons for electromagnetism, gluons for the strong nuclear force, and W and Z bosons for the weak nuclear force. However, there is one crucial missing element: mass. Every element has a specific mass, primarily determined by the number of protons and neutrons in its nucleus. But when looking at the particles themselves, it becomes clear that a proton's mass is much greater than the sum of the individual quarks inside it. More than 90% of an atom's mass comes from the energy and interactions within the particle, as described by Einstein's E equals mc squared equation. Despite this, quarks themselves do have mass, which posed a major question. Why do some particles have mass while others do not? This puzzle was tackled by British physicist Peter Higgs in the 1960s, who proposed that particles were initially massless, but acquired mass when a new energy field, the Higgs field, emerged. This field permeates all of space-time and interacts with particles, granting them mass. The Higgs boson, a particle associated with this field, would become the key to understanding mass. Though Higgs's theory was sound, it took nearly 50 years to confirm the existence of the Higgs boson. The search for this elusive particle required the use of powerful particle accelerators like the Tevatron at Fermilab in the US and the Large Hadron Collider at CERN in Europe. Despite the long and difficult journey, the discovery of the Higgs boson would prove to be a monumental achievement, helping to complete the Standard Model and deepen our understanding of the universe. Finding the Higgs boson was like searching for a needle in a haystack when you didn't even know what the needle looked like. However, in 2012, the Large Hadron Collider made this seemingly impossible task a reality. scientists confirmed the discovery of the Higgs boson, thereby proving the existence and functioning of the Higgs field once and for all. The particle earned its place in the Standard Model, and the field was recognized for its crucial role in shaping the early universe. A trillionth of a second after the Big Bang, the electroweak force split dramatically, ending the universe's perfect symmetry as the W and B bosons decayed into the photons of the electromagnetic force and the W and Z bosons of the weak nuclear force. But this was only the beginning of the symmetry breaking. The formation of the Higgs field around this time provided mass to both real and virtual particles that had spontaneously emerged during inflation and the electroweak splitting. While the W and Z bosons became massive, the photon and gluon remained massless and unaffected by the Higgs field. By a billionth of a second after the Big Bang, the quark era was fully underway, and the universe was populated with the necessary particles and forces to form stars, planets, and ultimately, life. The quark-gluon plasma that filled the early universe served as the primordial soup, from which all cosmic structures would eventually emerge. Fine-tuning, protons, neutrons, and antimatter. In the first millionth of a second. Our universe displays an astonishing variety. There are stars that burn hot and fast, others that last for trillions of years, barren rocky worlds, and occasionally habitable ones like Earth where diverse life forms exist. In the vastness of the universe, the potential for diversity seems endless. But alongside this variety, there are unchanging constants that govern how the universe behaves, regardless of location or observation. These constants of nature, such as the speed of light in a vacuum, gravitational constant, and others, have been revealed through scientific exploration. Numbers like the speed of light, 2.99792 times 10 to the power of 8 meters per second, or the gravitational constant, 6.67384 times 10 to the power of negative 11 meters per second squared per kilogram, might seem arbitrary, yet they are crucial to the universe's stability. The masses of fundamental particles too are fixed at specific values, though these constants defy explanation by the Higgs mechanism alone. The reason for these precise values is still a mystery, and even physicist Richard Feynman struggled with questions like why the fine structure constant, which defines electromagnetic force strength, is approximately 137 and not another number. These constants are finely tuned for the stability of the universe. If, for instance, gravity were weaker, the universe would be filled with hydrogen gas, preventing the formation of matter as we know it. If it were stronger, matter would collapse into black holes, hindering the formation of stars, planets, and life. These constants, though seemingly arbitrary, are key to the diversity and stability of the cosmos. But why are they tuned this way? The answer remains unclear. Some speculate it is a random coincidence, others believe it could be the result of a creator's influence, or perhaps our universe is just one of many, each with different constants, and only those that happen to have the right values can support life and cosmic variety. By 1/1,000,000th of a second after the Big Bang, the universe had cooled to 1,000,000,000,000 degrees Celsius, allowing gluons and quarks to interact for the first time. Protons and neutrons made of 3 quarks began to form, but the forces holding them together are complex. Quarks of the same type, like the 2 positively charged up quarks in a proton, naturally repel each other. To overcome this, the strong nuclear force mediated by gluons binds the quarks into stable hadrons. However, the internal structure of protons is even stranger than expected. While protons are made primarily of up and down quarks, they are constantly shifting. Occasionally, an up or down quark inside a proton can change into a charm quark and its antimatter counterpart. This transformation is brief, but it shows that protons are not static. In fact, much of the mass of a proton is made up of virtual particles that don't actually exist in a traditional sense. In the first millionth of a second, protons and neutrons were formed, but the universe's extreme conditions allowed them to easily change into each other, thanks to the weak force. As the universe cooled further and reached 1 second old, this ability to switch identities ceased, and protons and neutrons settled into stable forms. This process, known as freeze-out, was a key moment in shaping the future structure of the universe. The fine-tuned constants of nature, particularly the masses of quarks, began to play a significant role. Since down quarks are slightly heavier than up quarks, neutrons, which contain 2 down quarks, are slightly more massive than protons, which contain 2 up quarks. This mass difference would go on to have a profound impact on the formation of atoms, and eventually, life in the universe. As the universe continued to cool, the transition from heavier neutrons to lighter protons became the more energetically favorable process, rather than the opposite, which would require more energy. This slight mass difference ultimately caused an imbalance in the number of protons and neutrons in the universe, with about 7 protons for every neutron. This ratio became crucial for the formation of the universe as we know it. Protons form hydrogen and helium, which are the fuel for stars and the building blocks for all other heavier elements. The dominance of protons over neutrons allowed for elemental interactions, which led to the emergence of chemistry and eventually biology. If the down quark had been slightly lighter, the universe we know would be vastly different. If neutrons were lighter than protons, they would have been more abundant, and with more uncharged neutrons than protons, chemistry would have been severely limited. Hydrogen, consisting of only protons, would not have been stable over long periods, and although helium could form, it is chemically inert, which would hinder nuclear fusion. Without nuclear fusion, stars, galaxies, planets, and life would not exist. Fortunately, the universe favored protons, which played a critical role in shaping the cosmos we inhabit. However, another important imbalance arose around this time: the mysterious scarcity of antimatter. In the future, as we observe the sky, we may witness the destruction of an alien civilization. This may not be as dramatic as the explosion of a faint star, but it would release immense energy, potentially from a weapon powerful enough to obliterate an entire world. History shows that conflict, territoriality, and discord are common themes among human civilizations, and it's likely that other advanced civilizations would experience the same. As these alien civilizations advance technologically, they may turn to antimatter as a source of devastating energy. By isolating antimatter particles in a vacuum, these civilizations could create weapons with catastrophic potential. A single gram of antimatter can release as much energy as 90 kilograms of conventional nuclear fuel. In the context of an arms race, these weapons might one day be used in warfare, resulting in the annihilation of entire civilizations. The annihilation of antimatter with normal matter causes an energetic explosion, destroying everything in its path. The concept of antimatter, though, isn't confined to science fiction. In 1928, British physicist Paul Dirac predicted the existence of antimatter while working to reconcile Einstein's theory of special relativity with quantum mechanics. He realized that his equation suggested the existence of particles that were counterparts to electrons, leading to the prediction of the positron, or anti-electron. In 1932, American physicist Carl Anderson confirmed this prediction by detecting positrons in cosmic rays. This discovery paved the way for further research, and by the 1950s, the Bevatron Accelerator in California had detected antiprotons and antineutrons. In 1995, scientists created an antihydrogen atom, proving the existence of antimatter beyond theory. Today, antimatter is recognized in various contexts, from supernovae and black hole jets to the radioactive decay of potassium in a banana, which produces a positron approximately every 75 minutes. However, antimatter is still vastly outweighed by normal matter in the universe. In the Milky Way, there is no more than one antimatter particle for every quadrillion matter particles, according to physicists. If there were equal amounts of matter and antimatter, annihilation would have wiped out both, preventing the formation of stars, planets, and life. The reason for this imbalance remains a mystery. In the early universe, antimatter and matter were produced together, with pairs of particles forming spontaneously from energy fluctuations. In the dense conditions of the early universe, antimatter would quickly encounter matter, annihilating and turning back into energy. This process continued until the universe cooled, and no new quark-antiquark or lepton-antilepton pairs were created. However, as protons and neutrons began to form, they were accompanied by an equal number of antiprotons and antineutrons. Initially, there should have been an equal amount of matter and antimatter, but between 1/millionth and 2 minutes after the Big Bang, the balance shifted, and only one antimatter particle for every billion matter particles remained. To this day, physicists do not fully understand why this imbalance occurred. The broken symmetry that arose with the emergence of the weak force could partly explain this imbalance. Chien-Shiung Wu's 1950s experiments showed that quarks and antiquarks are treated slightly differently by the laws of nature. Though this difference is small, it is noticeable. However, scientists believe this alone is not enough to account for the dominance of matter over antimatter in the early universe. They propose that another, yet-to-be-detected and possibly extinct particle could have played a role. This idea stems from an asymmetry found in the Standard Model. While most particles and antiparticles have both right-handed and left-handed versions, there is an exception where parity symmetry is broken. Experimental physicists have only observed left-handed neutrinos, while antineutrinos are always right-handed. Where are the right-handed neutrinos and left-handed antineutrinos? Scientists speculate that these might have existed early in the universe, within the first millionth of a second, but decayed away. If they decayed preferentially into matter rather than antimatter, this could explain why matter triumphed. Although this theory is intriguing, it's hard to test without more information about these elusive neutrinos. We won't be able to gather more insight until the universe is around 1 second old. When we gaze into the furthest reaches of the night sky, we observe galaxies, nebulae, and quasars, distant supermassive black holes that consume matter and light at the cores of galaxies. Quasars reveal another fascinating feature known as the Lyman alpha forest. Due to the constant speed of light, distant objects appear older, and their light is redshifted, stretching into the red part of the electromagnetic spectrum. When examining the spectral signatures of these ancient quasars, astronomers notice sharp dips in the light, which are created by low-density hydrogen clouds in intergalactic space. As light passes through these clouds, some of it is absorbed, causing dips in the spectrum. These dips correspond to hydrogen clouds that we cannot see directly. Interestingly, these absorption features are more concentrated at high redshifts, suggesting that the early universe was full of these hydrogen clouds. This hydrogen became the birthplace of stars and galaxies, and was seated in the universe's first moments. By the time 1 second had passed, the universe had already reached a temperature of about 10 billion degrees Celsius. It was filled with particles from intense collisions, and the balance between protons and neutrons was established as the era of spontaneous particle creation ended. Particles possessing mass were endowed with it through the Higgs field, and the four fundamental forces, strong nuclear force, electromagnetism, weak nuclear force, and gravity, were fully operational, though still unstable in this high-energy environment. Up to this point, our understanding of the universe's first second has been based largely on theoretical physics. Our current technology struggles to replicate the extreme conditions of the early universe. However, we are now entering a phase of the universe's history that can be studied more directly by experimental physicists and astronomers. In Antarctica, a remarkable project is underway. The IceCube Neutrino Observatory, constructed by drilling holes into the ice, has created a network of detectors buried deep within the Antarctic ice. This unconventional design allows the observatory to study neutrinos, some of the most elusive particles in the universe. Neutrinos were first proposed in the 1930s by Wolfgang Pauli, who noticed missing energy in the decay of neutrons. He hypothesized that an invisible particle was responsible for this discrepancy. In 1951, American physicists Clyde Cowan and Frederick Rhines set out to detect these particles, and in 1956, they succeeded, confirming the existence of neutrinos. Today, scientists continue to study neutrinos both by producing them in particle accelerators and using detectors in remote locations like the IceCube Observatory. These ghostly particles offer a unique opportunity to learn about extreme cosmic events, such as supernovae, and to probe the very early moments of the universe. The explosion sent atomic debris racing through intergalactic space at nearly the speed of light. Among this debris were countless neutrinos emitted during the blast, and in 1987, scientists in Japan were fortunate enough to detect 11 of these elusive particles. While this may seem insignificant, the ability to observe the supernova through neutrinos marked the beginning of a new era in multi-messenger astronomy. By using gravitational waves, telescopes across various electromagnetic frequencies, and neutrinos, astronomers can now jointly study some of the universe's most extreme and enigmatic events. Additionally, neutrinos allow us to investigate objects that light cannot penetrate, as they interact so minimally with matter that they pass through everything, from nebulae and stars to entire planets. Their ability to interact only with the weak force and gravity makes them ideal for exploring some of the universe's earliest moments. After the Big Bang, when matter was first forming, the universe was too dense and hot for photons to travel freely for hundreds of thousands of years, rendering it completely opaque. Standard telescopes, which rely on photons, cannot probe this plasma, so scientists must turn to neutrinos for insights. In the first moments following the Big Bang, neutrinos and antineutrinos were part of the hot, energetic universe, colliding with matter. But after about 1 second, as temperatures dropped to 10 billion degrees Celsius, neutrinos moved slowly enough to escape without interacting with other particles. They broke free, leaving a trace of their passage through the universe. This imprint, called the cosmic neutrino background, would represent the universe just 1 second after its birth, giving us a glimpse of the cosmos 380,000 years earlier than what we can currently observe. However, these primordial neutrinos are far more elusive than their high-energy counterparts. While there are about 100 billion high-energy neutrinos per cubic centimeter of space, only about 300 from that early time are thought to exist. To detect them directly, we would need to build instruments with billion-fold precision, or find a way to study their impact on the cosmos. These early neutrinos are thought to have caused small disruptions in the distribution of matter and energy, altering the temperature in certain regions of space. Over 13.8 billion years, these patches have expanded, forming large-scale cosmic structures. By analyzing these patterns in the distribution of galaxies, we may be able to detect echoes from the universe's infancy. This mystery is not the only one rooted in the universe's first second. Take TON 618, for example. Located about 18.2 billion light-years away, it is one of the brightest objects in the universe, burning about 140 trillion times brighter than the Sun. Despite its enormous brightness, TON 618 harbors one of the largest known black holes. This supermassive black hole has a mass around 66 billion times that of the Sun, making it over 15,000 times more massive than Sagittarius A, the black hole at the center of the Milky Way. Its size is so immense that its gravitational pull causes matter to fall into it at speeds exceeding 10,000 kilometers per second, creating an intensely hot accretion disk that glows brightly. While TON 618 is the largest we've found, supermassive black holes, with masses over 100,000 times that of the Sun, are common at the centers of large galaxies and are believed to have played a major role in the formation and evolution of these galaxies. These black holes grow by consuming stellar material from their surroundings. However, astronomers have noticed something odd about the timing of these supermassive black holes. Many of these giants appear to have formed just a few million years after the Big Bang, at a time when star formation models suggest there should not have been enough stars to feed such early black holes. Some of the supermassive black holes we've found grew to masses billions of times that of the Sun in under a billion years, despite models predicting only a few 100,000 solar masses could have formed by then. One possible explanation for this is a theory proposed by Stephen Hawking in 1971, long before the discovery of these early supermassive black holes. Hawking suggested that black holes could form not from stars, but from density fluctuations in the very early universe. He called these objects primordial black holes. During the radiation-dominated era, inhomogeneities in the early universe, essentially clumps of matter, would have resulted from inflation and reheating. Gravity could have caused these regions to collapse, forming black holes. This process would have only been possible in the brief 1-second window after the Big Bang, before the universe cooled enough that gravity could no longer pull matter together. After that, black holes would only form from dying stars, but primordial black holes might explain the supermassive black holes observed today. However, we lack detailed knowledge of when these black holes could have formed, and how large they might have grown in that short time frame. The later a primordial black hole forms, the larger it could become, with estimates ranging from minuscule objects the size of a speck of dust to gargantuan ones 100,000 times the mass of the Sun. How can we detect and study these primordial black holes? One option is to look for signs of their destruction. In the 1970s, Stephen Hawking proposed that black holes could lose mass through a process known as Hawking radiation. This radiation would cause smaller black holes to shrink and eventually explode in a burst of energy equivalent to millions of megaton hydrogen bombs. Black holes with masses under 100 billion kilograms would have decayed by now, so scientists are using instruments like the Fermi Gamma Ray Telescope to search for these explosive events. Other potential approaches to searching for these elusive primordial black holes involve looking for microlensing effects and the magnification of stars and galaxies as the black holes pass in front of them. Another method is to detect the destruction of dense stars caught in the gravitational wells of these primordial black holes. However, these studies have so far only managed to exclude certain size ranges for primordial black holes, progressively narrowing the range of possibilities for their size and formation timeline. Yet, astronomers remain optimistic. The next generation of advanced telescopes will continue the search with greater reach and accuracy. The James Webb Space Telescope is currently investigating the early universe, looking for some of the first stars and galaxies, and in doing so, it will also search for primordial black holes that could have influenced their formation. Meanwhile, the Laser Interferometer Space Antenna, LISA, set to launch in the next decade, will scan space for gravitational waves, some of which may originate from primordial black holes that have been traveling through the universe since they first formed, barely 1 second after the Big Bang. Big Bang nucleosynthesis, the first minute. On December 5th, 2022, at the National Ignition Facility in California, humanity achieved a groundbreaking feat. Scientists focused 192 laser beams into a 1 centimeter long gold cylinder containing a small fuel pellet made of 2 hydrogen isotopes, deuterium and tritium. When the laser energy hit the capsule walls, it heated them to about 3 million degrees Celsius, hotter than the surface of the sun. This caused the capsule to emit X-rays, which then bombarded the pellet, compressing the fuel at a rate of 400 kilometers per second. The compression created pressures 100 billion times greater than atmospheric pressure in less than 10 billionths of a second, causing deuterium and tritium atoms to fuse into helium, releasing high-energy neutrinos and other energy in the process. In total, 2.05 megajoules of energy entered the cylinder, while the fusion reaction produced 3.15 megajoules, marking the first successful demonstration of a productive nuclear fusion reaction. Though fusion itself has been used for weapons since the 1950s, this marked the first time we've achieved a fusion reaction that released more energy than was used to start it. While this experiment was small-scale, providing enough energy to boil 20 kettles, it heralds a potential new era of clean, efficient energy generation. However, this process has been naturally occurring in the cores of stars for billions of years. In fact, the universe's physics had already figured out fusion within its first minute. Humanity has long been fascinated by the idea of transforming one substance into another, whether it's creating flowers from thin air or turning base metals into gold. The early universe was full of such transformations, driven by unsettled fundamental forces that led to chaotic changes, and even today, such processes continue. One example is radioactive decay, where atomic nuclei break apart, transforming elements into lighter ones, driven by the weak force. This occurs predictably and regularly in elements like carbon-14, used in carbon dating, technetium-99, used for medical imaging, and uranium-235, used as nuclear fuel. Radioactive decay happens spontaneously under ambient conditions, when atomic nuclei are unstable. In contrast, nuclear fusion, where atomic nuclei combine to create heavier elements, is much harder to achieve. The identity of an element is determined by the number of protons and neutrons in its nucleus. Hydrogen, for example, has one proton, and its isotopes, deuterium and tritium, have 1 and 2 neutrons respectively. When 2 protons combine, they form a helium nucleus, with helium-3 having 1 neutron and the most stable form, helium-4 having 2 neutrons. The strong nuclear force binds protons and neutrons together, but since protons have a positive charge, they repel each other due to the electromagnetic force, making it difficult for them to come together. This requires immense heat and pressure, such as in the cores of stars or within the gold capsule in the experiment. Only under such extreme conditions can the strong nuclear force overcome electromagnetic repulsion and allow elements to fuse into new ones. Creating even heavier elements requires even more extreme cosmic events, such as supernovae or star mergers. While scientists have a good understanding of how nuclear fusion occurs inside stars, turning hydrogen into helium and heavier elements, they still seek to explain how the first nuclei of deuterium and helium formed before stars existed. To understand this, we must look to the very first minute of the universe, before stellar fusion began. Around 1 microsecond after the Big Bang, when the universe cooled to around 10 trillion degrees Celsius, quarks bound together to form protons and neutrons, which would later become the building blocks of all elements. However, it would take another 100 million years for the first stars to form and begin nuclear fusion. So, how did those first nuclei come together? In 1948, American PhD student Ralph Alpher, working with his supervisor George Gamow, proposed a theory that would later be known as Big Bang nucleosynthesis. While Alpher's work was groundbreaking, it was overshadowed by Gamow's insistence on adding another author, Hans A. Bethe, who had no role in the development of the theory. The Alpha Beta Gamma paper became a cornerstone of our understanding of prestellar fusion and how high temperatures in the early universe could turn hydrogen into helium through deuterium intermediates. Protium, the lightest hydrogen isotope, existed as soon as quarks formed protons. However, it took longer for neutral hydrogen atoms, consisting of protons and electrons, to form. Around 10 seconds after the Big Bang, the universe cooled enough for deuterium nuclei, 1 proton and 1 neutron, to form. However, the conditions were still so hot that deuterium nuclei were unstable and would break apart if struck by photons. This instability, known as the deuterium bottleneck, prevented nucleosynthesis from progressing beyond the fusion of 1 proton and 1 neutron until the universe cooled enough for more stable reactions to occur. Only after approximately another 300 seconds do the temperatures cool enough for deuterium to stabilize and allow the formation of additional elements. Initially, deuterium, which consists of 1 proton and 1 neutron, can fuse with individual protons under the immense compressive force of the entire universe. This fusion creates for the first time a stable new element, helium-3. From this point, the next creation is the more common helium-4. composed of 2 protons and 2 neutrons. Helium-4 nuclei are the most stable atomic nuclei in existence and are incredibly difficult to break apart. Because of this, and the conditions in the first few hundred seconds, most of the free protons in the early universe were absorbed into helium and didn't form any further elements. Predictions based on the initial ratio of protons to neutrons and the available energy at this time suggest that this process would result in a universe that is about 25% helium by mass, a figure that aligns closely with what we observe. Even 13.8 billion years after the initial burst of helium creation, following the birth and death of countless stars, the universe still contains about 23% helium. This observation strongly supports Alpher's theory. Furthermore, it serves as another example of the fortunate fine-tuning of the universe's initial conditions. We know that if the proton-to-neutron ratio had been different, much of the universe's matter would have decayed into neutral, unreactive neutrons and helium. However, if the matter had been more compact during Big Bang nucleosynthesis, even more helium would have formed, rendering the universe composed mostly of helium, with little chance for chemistry to occur afterward. This would have led to a universe without stars, galaxies, or life as we know it. Fortunately, this wasn't the case. As many hadrons settled into stable helium nuclei, the universe still contained latent energy that could potentially be used for further fusion. At this point, the cosmic race began to create as many new elements as possible before the ambient energy of the universe dropped too far. Eventually, after about 1,200 seconds, or 20 minutes into the universe's existence, the nuclear fusion process slowed and halted. While still incredibly hot by human standards, it was too cold for any more nuclei to form. By this time, only 4 elements existed: hydrogen, helium, lithium, and beryllium. Due to the instability of beryllium nuclei, only the first 3 elements survived long enough to witness the formation of the first stars, which would later serve as the furnace for the creation of the other 98 naturally occurring elements in the modern universe. At this stage, the ratio of hydrogen to helium was 12 to 1, with a billion photons for every particle of matter. These basic ingredients would now set the stage for the formation of everything else, including the deuterium and tritium fused together in California in 2022, which were originally created in the heat of the early universe 13.8 billion years ago. The first molecules. The first 100,000 years. Life in the universe is a remarkable chemical phenomenon, and as far as we know, this chemical miracle has occurred in only one place: on a wet, rocky planet orbiting an average yellow star, located on the inner edge of one of the Milky Way's smaller spiral arms. But how did life come to exist on Earth? Despite a well-preserved fossil record spanning over 3 billion years, the exact moment of biological origin, the spark of life, remains a mystery. Biologists agree that living organisms are made of organic molecules composed of carbon, oxygen, and hydrogen. Moreover, they've discovered that all living things share a common chemical blueprint in the form of DNA and RNA, which are made up of repeating units known as nucleobases. Cytosine, guanine, adenine, thymine, and uracil form a universal code for encoding the information needed to grow everything from a leaf to a hair follicle. But where did these molecules come from? One theory is that the early Earth provided the perfect conditions for assembling organic molecules and nucleobases from scratch. However, another theory suggests that the ingredients for life weren't created on Earth, but instead in the stars, deep within space. Indeed, evidence is accumulating to support the idea that the building blocks of life are present far beyond our planet. In 1969, American astronomers at the National Radio Astronomy Observatory in West Virginia detected the characteristic vibrations of formaldehyde molecules containing carbon, hydrogen, and oxygen deep in interstellar space. Since then, over 250 complex organic molecules have been identified in interstellar clouds and in the material surrounding stars. These molecules, including aldehydes, alcohols, acids, and amines, are fundamental components of larger molecules that form life. In 1864, an even more striking clue about the potential for life in outer space arrived on Earth. A meteorite fell near the town of Orgueil in southern France, breaking into about 20 pieces. When scientists analyzed the Orgueil meteorite, its composition was similar to peat, sparking debates about whether this organic matter could have a biological origin. While no biological structures were found, a reanalysis of the meteorite nearly 100 years later revealed adenine and guanine nucleobases, identical to those found in DNA and RNA. Further studies of other organic-rich meteorites, such as the Murchison meteorite from Australia, the Murray meteorite from Kentucky, and the Tagish Lake meteorite from Canada, have uncovered additional nucleobases that are found in Earth's biology, along with others not present in our life forms. Though we still don't have a definitive answer, these discoveries suggest a surprising truth about the cosmos. The universe itself has the ability to build molecules and perform remarkable chemistry. This chemistry began in the infant universe, less than 100,000 years after the Big Bang. By this time, the intense process of elemental creation during Big Bang nucleosynthesis had ended after just 20 minutes of cosmic existence, as the universe expanded and cooled. With temperatures no longer high enough to sustain nuclear fusion, the universe remained a hot, dissociated plasma. The cosmos was still denser than air, and temperatures were too high for electrons to be captured by elemental nuclei. There was still more energy than matter in the universe, and it would take tens of thousands of years for the universe to cool, sufficiently for any change to occur. Yet even in this chaotic environment, something was happening. One example is helium hydride, an unstable ion of helium bonded with hydrogen, which was first created in labs in 1925. In 1978, astrochemist John H. Black at the University of Minnesota predicted that helium hydride could be found in abundance in space, particularly in planetary nebulae. These nebulae form when red giant stars explode, and the interaction between ionized helium and neutral hydrogen leads to the formation of helium hydride ions. However, despite extensive searching, this molecule remained elusive until 2019, when an innovative telescope succeeded in detecting it. Nowadays, most telescopes are either positioned on the ground, typically on high mountaintops to minimize light pollution, weather interference, and atmospheric distortion, or they are sent into space to avoid these issues entirely as they orbit the Earth or the Sun. However, the Sophia Observatory took a unique approach. It featured a 2.7 meter wide mirrored telescope, mounted at the back of a specially modified Boeing 747, flying at an altitude of over 43,000 feet. At this height, the telescope's instruments could benefit from many advantages of a space telescope, as they were above most of the Earth's atmospheric water vapor. This allowed them to observe wavelengths of light that water vapor typically absorbs. The telescope was also connected to a far-infrared receiver called GREAT, which had the resolution needed to detect the faint overlapping signature of helium hydride ions in deep space. Ultimately, the detection came after 3 days of observations of the planetary nebula NGC 7027, located about 3,000 light-years away in the direction of the Cygnus constellation. It is one of the brightest nebulae in the sky. In this energetic interstellar environment, as predicted by John Black 4 decades earlier, helium hydride forms and leaves its distinct signature in the nebulous spectrum. This discovery marks a significant achievement in both experimental and theoretical chemistry, as well as astronomical innovation, but its implications extend even further. The conditions inside this distant nebula resemble those that prevailed throughout the entire universe during its first tens of thousands of years. While the helium hydride found here is not primordial, proving its formation in such an environment sheds light on its potential in the early cosmos. Big Bang nucleosynthesis was highly efficient in creating atomic nuclei, but for hundreds of thousands of years afterward, the cosmic energy was still too high for hydrogen, deuterium, and helium to combine with electrons and form neutral atoms. However, when the temperature dropped to around 4,000 Kelvin, these nuclei could combine in a specific order, based on their ionization potential. This is why helium is considered the most noble of the noble gases. Its extremely stable configuration makes it highly inert. In the early universe, when ions predominated, helium's ability to attract electrons allowed it to form the first neutral atoms, but this stability was short-lived. As protons couldn't capture electrons to form hydrogen atoms, they interacted with helium, and under the pressure of these protons, helium formed the universe's first chemical bonds, creating unstable helium hydride ions. These fleeting molecules paved the way for the formation of other molecules and the birth of space chemistry, roughly 100,000 years after the Big Bang. Today, the field of astrochemistry studies the types of molecules we can expect to find in space and how they form. Many molecules common on Earth, such as water and ammonia, are also found in the cosmos. Others, such as dihydrogen monochloride H2Cl+, or hydroperoxyl HO2, are far more exotic. Though many are yet to be discovered, whatever they turn out to be, their existence ultimately traces back to the helium hydride ions, formed in the universe's first 100,000 years. The electromagnetic force is about 100 times weaker than the strong force that binds hadrons and atomic nuclei together, meaning the universe's conditions must be significantly less energetic for electromagnetism to capture the highly charged electrons and bring them into stable orbits. After 380,000 years of cosmic expansion, the temperature finally drops to around 3000 Kelvin, allowing electrons to join atomic nuclei and form the first stable atoms. When this happens, the entire universe undergoes a profound transformation. Electromagnetic forces pull electrons into stable orbits around atomic nuclei. No longer free to roam, electrons now become tightly bound to positively charged counterparts, creating empty space for the first time since matter's creation. Photons, previously trapped in a maze of particles, can now escape, traveling in straight lines without striking other particles. This marks the first time light can truly penetrate the universe. What was once opaque now becomes transparent, what was plasma turns into gas, and what was broken is now whole. For the first time in the universe's history, we can finally see what is happening. Scientific breakthroughs rarely happen by chance, let alone those that lead to Nobel Prizes. Typically, they are the result of years of hard work, research, and dedication. However, in 1978, the Nobel Prize in Physics defied tradition, as it was awarded to two men whose groundbreaking discovery was largely accidental. The stage for this serendipitous discovery was set in the early 1960s in Holmdel, New Jersey, where Bell Labs had built a 20-foot horn-shaped antenna. A few years after its construction, a new satellite system replaced the old, making the antenna obsolete. Yet, Bell Labs repurposed the antenna for research, opening it up to astronomers Arno Penzias and Robert Wilson, who were studying radio signals coming from the space between galaxies. But when they began their observations, the duo was baffled by a persistent low-level radio hiss. They ruled out interference from nearby New York City or military installations, and confirmed it wasn't originating from anywhere in the Milky Way or beyond. The signal seemed to be coming from all directions. They initially assumed the noise was due to an instrument error. Upon inspecting the antenna, they discovered it was home to a number of pigeons, and their droppings, described as a white dielectric material, could be emitting heat that caused the noise. After unsuccessful attempts to humanely relocate the pigeons, the researchers resorted to more drastic measures, cleaning the antenna of both birds and droppings. Yet the hissing continued. With all other sources of error eliminated, Penzias and Wilson considered the possibility that the radio noise was coming from the entire sky. They contacted astronomer Robert Dicke at Princeton University, who solved the mystery. Dicke had been working on a theory of atom formation in the early universe, suggesting that the Big Bang was cyclical, with atoms from a previous universe being torn apart in a fiery compression before being reassembled as the universe expanded and cooled. His theory predicted that this recombination would allow the universe to become transparent and release light for the first time. This light, initially in the visible spectrum, would be stretched by cosmic expansion into the microwave wavelengths that Penzias and Wilson had accidentally discovered. Though Dicke had planned to search for it himself, Penzias and Wilson had beaten him to the punch. A decade later, they were awarded the Nobel Prize for discovering the cosmic microwave background CMB, while Dicke was not. Regardless of who first identified the CMB, its discovery marked a monumental shift in our understanding of the Big Bang. The detection of the microwave glow, now redshifted to 2.7 degrees above absolute zero, provided definitive evidence that the universe began in a hot, dense state. Though this light was emitted 380,000 years after the Big Bang, it confirmed the theories of cosmic evolution in the intervening period and offered clues about the future of the universe. Instruments designed to study the CMB later found tiny variations in its temperature, slightly warmer or cooler spots by a few hundred thousandths of a degree. Mapping the CMB became a priority for missions like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck Telescope, which produced increasingly detailed images of the universe's energy and density variations from 380,000 years ago. These variations correspond to regions of higher matter density, which attract even more matter, ultimately growing into dense areas that trigger the formation of the first stars and galaxies within 100 million years. The CMB's variations help astronomers predict where these structures would form. In the early universe, when it was still filled with opaque plasma, sound waves could travel through the dense matter. These waves were generated by the interplay of forces, gravity pulling matter inward while photons exerted outward pressure. As a result, concentric ripples formed, resembling the waves created by raindrops in a pond. Cosmologists call these sound waves baryonic acoustic oscillations. However, when the universe cooled enough for atoms to form at around 3000 Kelvin, the waves were frozen in place and the matter at their edges was left behind. Today, these frozen ripples can still be seen in the large-scale structure of the universe. The baryonic acoustic oscillations span roughly 150 megaparsecs, about 500 million light years, and serve as a standard ruler for measuring the expansion of the universe. With this knowledge, in a universe now visible to our instruments, we can model how events have unfolded and predict how they will continue to evolve. The universe's first light may have stretched and faded, becoming a faint shadow of its original form, but it will remain visible for trillions of years before completely disappearing from our view. This provides future cosmologists ample time to unlock its mysteries. A tiny spark of light ignites in the vast emptiness of space. One by one, small points of light appear. Soon a cluster grows, swelling and becoming brighter as more young stars are born. Over the course of a few billion years, this cluster becomes large and massive enough to begin rotating. Its angular momentum stretches it into a disk, spinning at over 200 kilometers per second, completing a full rotation every 250 million years. As this young spiral galaxy travels through intergalactic space, it pulls in smaller clusters along its path. Collisions with other galaxies result in mergers, fueling rapid star formation. About 10 billion years ago, our Milky Way galaxy reached its prime. For billions of years, massive stars in the spiral arms of the Milky Way ignited, burned brightly, and exploded, scattering their spent fusion products back into the galactic cloud. This enriched gas, full of heavier elements, became the building blocks for a new generation of stars and the first planetary systems. A star was born on the outer edge of a spiral arm, some 25,000 light years from the galactic center, around 4.6 billion years ago. Much like the galaxy itself on a smaller scale, dust and gas formed a flattened disk around it. Dust clumped into pebbles, pebbles into boulders, and eventually these boulders became rocky planets. After several catastrophic collisions, these rocky worlds settled into stable orbits that will remain intact for the next 4.5 billion years. On the third of these planets, the heat from its violent formation dissipated, water condensed to form oceans, and tectonic activity began to recycle the planetary surface. Somewhere in those oceans, life sparked into existence, evolved and adapted, filling this unique world with a new form of creation. Chemistry transformed into biology, and a vast array of life forms thrived in the sea, on land, and in the sky. And then, from seemingly nowhere, a sentient mind emerged, capable of contemplating its place in the universe. Despite our understanding of the broad sequence of events that led to the formation of the Milky Way, the Sun, Earth, life, and humanity, gaps remain in our cosmological knowledge. How did the primordial soup of atoms created just a few 100,000 years after the Big Bang eventually lead to everything we see today? Was this path inevitable, or could the universe have followed a different course? When we simulate cosmic evolution based on the matter and energy that existed during the formation of the cosmic microwave background CMB, we find a universe that is subtly different from the one we know. There are fewer galaxies, less active star formation, and delayed planetary formation. In these simulations, life might be delayed, or entirely absent. Clearly there's something missing, a final puzzle piece that completes the picture. Unfortunately, that missing piece is something cosmologists cannot yet observe. 380,000 years after the Big Bang, light finally escapes its prison of matter. Photons can travel freely through the expanding universe, but they lose energy as it stretches. While the universe is no longer opaque, it is still dark. The intense energy of formation has diminished, and it will be millions of years before nuclear fusion begins to concentrate energy once more. These are the dark ages of the universe, a time with little to see, though much is still happening. It is during this period, especially in the first million years of cosmic history, that dark matter is believed to play a pivotal role in shaping the future of the universe. The concept of dark matter emerged in 1933, when Swiss astronomer Fritz Zwicky was studying the Coma cluster of galaxies, about 320 million light years from Earth. The galaxies seemed to be moving too fast for the cluster to remain intact. The masses of the galaxies, based on their visible stars, were about 10 times less than needed to explain their motion. To resolve this discrepancy, Zwicky suggested the presence of an unseen mass scattered throughout the visible matter. He called this invisible mass Dunkle Materie, or dark matter. Although progress was slow for decades, in the late 1970s, astronomer Vera Rubin made an important observation while studying the rotation of the Andromeda Galaxy. She found that stars on the outer edges of the galaxy were moving just as fast as those near the center, which contradicted expectations. This suggested that the visible matter accounted for only a small fraction of the galaxy's total mass. Rubin calculated that only about 15% of the mass in the Andromeda Galaxy was visible, with the rest being invisible dark matter. Later observations revealed that most galaxies, including our own, are surrounded by large halos of dark matter. Current estimates suggest the Milky Way's dark matter halo is up to 15 times larger than its visible extent. Today, astronomers are convinced that dark matter plays a crucial role in shaping the universe, even though it remains undetectable. Larger studies indicate that dark matter may outweigh ordinary matter by a ratio of 6-1, potentially always having done so. But what dark matter is remains a mystery. One possibility is that dark matter consists of ordinary objects made of normal baryonic matter, such as black holes, neutron stars, or brown dwarfs, which are difficult to detect. These objects, collectively known as MACOs, may have been overlooked due to their elusive nature. However, as our observational tools improve, the chances of detecting such objects decrease. As a result, cosmologists now favor the idea that dark matter is made of weakly interacting massive particles, WIMPs, a new type of particle outside the standard model. These particles would only interact with normal matter via gravity, but in sufficient quantities they would account for the missing 85% of the universe's mass. The hunt for the elusive WIMPs continues both in particle accelerators and throughout the cosmos. Yet with so little to go on, the journey ahead could be long. Whether dark matter is composed of MACOs, WIMPs, or something entirely different, it's likely that dark matter has been present since the very beginning, lingering in the shadows of visible matter since the universe's first fractions of a second. It was during the cosmic dark ages, around 1 million years after the Big Bang, that dark matter began to shape the structure of the universe. The cosmic microwave background suggests that matter and energies were distributed unevenly at the time of atomic recombination, and dark matter likely followed this pattern. Over these darkened millennia, this unseen mass began to take form. Gravity pulled dark matter together, causing it to clump more rapidly and densely than expected for normal matter. This created invisible gravity wells that would pull invisible matter, leading to the formation of cosmic filaments, nodes, and clusters of gas that would eventually become the first stars and galaxies. From this moment, the evolution of the universe as we know it became inevitable. Everything that occurred in the first million years of cosmic history laid the groundwork for the next several billion years of astrophysical creation. The universe cooled to a point where known physics took over, and the 4 fundamental forces became distinct, governing all interactions. The distribution and nature of matter were set, providing the raw materials for stars, galaxies, the birth of chemistry, and ultimately life. However, this process wasn't entirely predictable. For 8 billion years, the universe's evolution followed the expected course. But between 5 and 6 billion years ago, just before the formation of our solar system, something changed. Identifying this shift made it clear that our understanding of the universe's balance was incomplete. This dramatic change was first observed around 25 years ago when astronomers were studying supernovae at different distances across space and time. Certain supernovae, known as standard candles, explode with a predictable brightness, making them useful for measuring cosmic expansion. Their light becomes redshifted as space expands. But in 1998, astronomers noticed that the supernovae from the last 5 billion years were redshifted more than expected, indicating they were moving away from us faster than anticipated. This same acceleration was observed in baryonic acoustic oscillations in galaxy clusters. Even more startling, the rate of expansion itself seemed to be speeding up. The leading explanation for this accelerating phase of the universe's evolution is dark energy. For the entire history of our solar system, we've been living in an era dominated by dark energy. Like dark matter, cosmologists still don't fully understand what dark energy is. When Einstein developed his theory of general relativity, he introduced the concept of the cosmological constant, which represented the inherent energy of empty space. As space expanded, more of this energy appeared, potentially driving further expansion. While general relativity later discarded the need for this constant, the idea resurfaced to help explain dark energy. The challenge remains that we don't understand why such an intrinsic energy should exist at all. If the answer isn't found on cosmic scales, perhaps the very small scales of quantum theory hold a clue. Quantum theory predicts the phenomenon of vacuum energy, where virtual particles spontaneously appear and disappear due to quantum fluctuations, exerting pressure that causes expansion. While this is a promising idea, calculations based on vacuum energy at larger scales are far too high to explain the observed cosmic expansion. As a result, some cosmologists are now considering an entirely new type of energy field called quintessence. Quintessence behaves differently from normal matter and energy, being capable of both attractive and repulsive forces, and could change its characteristics over time. However, without experiments or observations that can directly probe or confirm its existence, we are left in the dark, watching as time passes and space continues to expand. Thus, whatever its true nature, we live in a universe composed of approximately 68% dark energy, 27% dark matter, and less than 5% normal matter. It is with these elements that our universe has evolved over 13.8 billion years, adhering to the laws and constants that were established in its very first moments, within the first 10 tridecillionths of a second after the Big Bang.